In the beginning, there was fire, a universe only seconds old, a storm of creation so dense and hot that space itself burned with light. Particles collided, annihilated, reappeared, a cosmic rainstorm where existence itself flickered in and out like sparks in the wind. As the universe cooled, most of those sparks vanished forever. Matter and antimatter destroyed one another in a perfect, violent balance, leaving behind only a fragile remainder, a thin veil of particles from which everything we know would one day arise. Among them drifts one of the strangest survivors, a single, stubborn fragment of reality. Invisible, silent, almost eternal. It should have disappeared long ago, and yet it has not. Across billions of years, it has outlasted stars, outlived galaxies, and passed unchanged through the birth and death of entire worlds. The cosmos grows colder, space stretches wider, light itself dims. But this particle remains like a grain of memory that refuses to fade. Its endurance is not just a curiosity, it is a challenge to the very way we understand existence. In a universe that seems destined for decay, what does it mean for something to refuse annihilation? Every equation says that time must consume all things, that nothing can truly last forever. And yet here, hidden in the heart of every atom, is a quiet rebellion. In a universe built on the law of impermanence, this particle is a defiance, a riddle written into the fabric of reality. If you are new here, join the journey, like, subscribe, and let's begin. In the wake of the Second World War, a new age of science dawned. Humanity, shaken by the atomic bomb, turned its eyes inward into the very heart of matter itself. The war had shown what power lay hidden in the nucleus of the atom, and in the aftermath, a generation of physicists set out to decipher the deep rules that governed this invisible machinery. Nuclear reactors became both weapons and laboratories. Particle accelerators grew like strange new temples, and detectors were lowered into mountains, oceans, and caverns in search of particles no eye had ever seen. Among these quiet hunts, one question began to grow like a splinter in the mind of physics. If the universe is ruled by decay, if every system slides toward disorder, then should not even the most basic particle eventually dissolve into something simpler? This was not a philosophical daydream, but a scientific prediction. The standard model of particle physics, a cathedral of equations that described almost every known particle and force, quietly hinted that protons, the very bricks of matter, might not last forever. Given enough time, they should collapse into lighter particles, releasing a faint flash of energy as they died. But time is a trickster, and nature does not give up its secrets easily. In the early 1950s, physicists Clyde Cowan and Frederick Raines devised a daring experiment to detect the most elusive particle ever theorized, the neutrino. If protons were fated to decay, if nuclear reactions inside stars were quietly shaping the destiny of matter, then neutrinos were the ghostly witnesses of that process. Cowan and Raines built their detector near the Savannah River nuclear reactor, a place where an immense stream of neutrinos flowed invisibly through the Earth. Their instrument was simple but ingenious. Giant tanks of water, doped with cadmium, chloride, surrounded by detectors that would flash if a neutrino interacted. And then, against all odds, they saw it, a faint, almost imperceptible signal, a particle that had no charge, almost no mass, and could pass through a wall of lead a light year thick without stopping. The neutrino had been found. The world of physics erupted in celebration. Here was proof that nature held more invisible players than anyone had guessed. But alongside the triumph came a new unease. Neutrinos were supposed to be near massless, barely there. Yet they existed in almost unimaginable numbers. They streamed out of the sun by the trillions every second, passing through every living body, through oceans and planets, without leaving a trace. It was as if the universe was filled with a secret population of ghosts, and humanity had just learned their names. This discovery emboldened scientists to look deeper. If neutrinos were real, could proton decay also be real? Could matter itself be mortal? In the 1970s and 80s, as particle physics matured, massive underground experiments were built to catch a proton in the act of dying. The most ambitious of these was Super-Kamiokande in Japan, a cavern the size of a cathedral buried deep beneath Mount Ikanoyama. Inside, 50,000 tons of ultra-pure water were suspended in silence, watched over by 11,000 photomultiplier tubes, electronic eyes that could see a single flash of Cherenkov light. The blue glow emitted when a charged particle traveled faster than light through water. Scientists waited. Days turned to months. Months turned to years. Billions of protons quietly sat inside the tank, each one a ticking clock, each one expected to collapse eventually. If a proton decayed, the resulting shower of particles would create a tiny pulse of light, captured forever on the detector's digital memory. But the pulses never came. Instead, something stranger emerged. The detectors picked up other flashes, other tracks, particles behaving in ways no one had fully anticipated. Neutrinos from cosmic rays, muons streaking through rock, and occasionally, events that hinted that something was persisting, something that seemed to refuse to vanish. The silence of proton decay became almost as meaningful as its discovery would have been. It suggested that protons, and perhaps all baryonic matter, might be far more stable than theory had predicted. Their half-life was pushed farther and farther back, first to billions of years, then to 1032 years, then to 1034. Numbers, so vast they made the age of the universe, a mere 13.8 billion years, seem like the blink of an eye. What the detectors found was not the death of matter, but its stubborn endurance. Cloud chamber photographs from early accelerators revealed similar hints. Tracks of particles appeared where there should have been none, curling faintly in magnetic fields, leaving trails like handwriting across a dark plate. In some experiments, the expected annihilation never came. Particles lingered just a fraction, longer than they should have, as if time itself hesitated before erasing them. This was not a discovery that came with fireworks. It came with stillness, with the quiet realization that the smallest building blocks of reality might be immortal, that matter itself might be unwilling to let go. For the scientific community, this was both exhilarating and unnerving. If protons did not decay, if particles persisted beyond all prediction, then the universe would never reach a perfect equilibrium. Instead of dissolving into a featureless bath of photons, matter would remain, scattered and cold, but enduring. And so, as the 20th century progressed, particle physics found itself standing at a strange threshold. The deeper scientists probed, the more reality seemed to hold its ground. Every failure to detect proton decay, every stubbornly silent result, became its own kind of signal. It told a story not of death, but of persistence, a cosmic refusal to yield. It was here, in the quiet depths of laboratories, in underground caverns where human eyes never saw the sky, that the mystery first took shape. Somewhere in the fabric of the universe, a particle was resisting the universal rule of decay. Somewhere in the subatomic darkness, a fragment of matter had decided it would not vanish. And this was only the beginning. In science, there are discoveries that confirm what we expect. And then there are silences that thunder louder than any signal. The silence from proton decay experiments was deafening. For decades, physicists had trusted the Standard Model, a framework so elegant and precise that it seemed to describe nearly every particle and force in existence. It was a triumph of the 20th century, a theory that had predicted the W and Z bosons, neutrino interactions, even the Higgs field. And yet, at its edges, there was a quiet prediction that protons, the very foundation stones of atoms, should not last forever. Given enough time, they should transform into lighter particles, their energy dissipated into the fabric of the universe. But they did not. The detectors kept watching, waiting for a single flash of Cherenkov light that would mock the death of a proton. Instead, the tanks of water sat undisturbed. Not one event matched the predicted signature. The deeper scientists buried their detectors to escape cosmic noise, the clearer the message became. If protons decayed at all, their lifetime was staggeringly longer than theory had dared suggest. Not billions of years, not trillions, but numbers so enormous they could scarcely be imagined. This was the first great shock. Physics is built upon symmetries, upon patterns that repeat across scales, and decay is one of its most trusted rhythms. Neutrons decay outside of nuclei within minutes. Pions vanish in a fraction of a microsecond. Even the unstable isotopes of uranium and thorium slowly transmute, shedding their energy over geological epochs. The idea that protons might persist indefinitely was not just surprising, it was destabilizing. If protons were immortal, then the universe itself would never fully dissolve. The grand thermodynamic narrative, the story of entropy, had always suggested a final state, a heat death, where every star burns out, every black hole evaporates, every particle decays, and what remains is a thin, dark bath of radiation, stretching across an ever-expanding void. But now, this picture seemed incomplete. Matter would not fully vanish. Somewhere, in the far reaches of cosmic time, islands of protons would still exist. Cold, inert, drifting through the abyss, like embers that refuse to extinguish. For physicists, this was more than an abstract concern. If protons never decay, then the Standard Model is not just incomplete, it is wrong in one of its most subtle but profound ways. The quest for a grand unified theory, one that would unify the strong nuclear force with electromagnetism and the weak force, often relies on proton decay as a crucial prediction. The absence of decay called those models into question. It was as though nature had built a door and then locked it forever. The emotional weight of this silence grew heavier with every passing year. Scientists who had devoted their careers to waiting for a single proton's death began to face a strange truth. They might never witness one at all. The half-life estimates grew so long that no experiment could ever hope to run long enough to prove immortality. The only way to be certain would be to watch every proton in the universe for a span of time far greater than the universe's own age. An impossible demand. This was the second shock, the realization that some mysteries might remain forever, unresolved, not because they are beyond human intelligence, but because they are beyond human timescales. It left physicists with unsettling philosophical questions. What does it mean for matter to be eternal? If entropy is the law, if the arrow of time always points toward disorder, how can there be a piece of reality that resists it? Is the arrow of time truly universal? Or are there exceptions hidden in the subatomic world? Pockets where permanence is possible? This contradiction rippled outward into cosmology. If protons do not decay, then the distant future of the universe is not one of perfect uniformity. Instead, a slow, cold persistence stretches toward infinity. The stars will still die, the black holes will still fade, but the atoms themselves, hydrogen, carbon, oxygen, will remain scattered like unmelting snow across the black desert of space-time. It was both a comfort and a terror. Comfort, because it meant that something, however small, would survive the death of everything else. Terror, because it suggested that the universe is not a place of perfect symmetry and closure, but one that clings to fragments of its past forever. For those who had believed that science could one day write the final equation of reality, this was a humbling moment. The refusal of the proton to vanish was not just a technical puzzle. It was a reminder that the universe is under no obligation to answer human questions on human timescales. And so, in quiet laboratories and mountain caverns, a new narrative began to take shape, one where the story of matter was no longer a brief flare between two eternities of nothingness, but something stranger, something longer, something that might stretch without end. The silence was no longer merely an absence of data. it had become a message, and the message was clear. The smallest bricks of reality may be eternal. The universe may carry its memory forever. But if this was true, it would upend not only particle physics, but the way humanity understands time itself. The shock had given way to a deeper unease. What other assumptions might be wrong? What other invisible rules of the cosmos might resist the grand narratives humans tell about birth and death, beginning and ending? This was no longer merely an experimental anomaly. It was a philosophical wound, a challenge to the deepest assumptions about how reality works. And the only way forward was to look deeper still, to build better detectors, ask better questions, and follow the riddle into darker and stranger places. The hunt was no longer simply about whether protons decay. It had become a search for the ultimate fate of existence. And somewhere, far below the mountains, in the darkness of detectors that never sleep, the universe continued its long, slow refusal to give up its secret. To search for something that almost never happens requires building instruments that are almost impossible to imagine. Detecting proton decay is not like looking for a planet, a star, or even a particle collision. It is the attempt to catch a single flicker of light that might not appear for billions of years. And so, humanity began to dig. Across the late 20th century, enormous underground caverns were hollowed out beneath mountains, inside old mines, and under kilometers of rock. The reason was simple. The Earth's crust would shield these experiments from the noise of the outside world. The endless rain of cosmic rays and radiation that would overwhelm a detector at the surface. In these dark sanctuaries, physicists built detectors that resembled cathedrals. Their walls were lined with photomultiplier tubes, electronic eyes so sensitive they could see the faintest glimmer of Cherenkov radiation, the bluish light produced when a charged particle streaks through water faster than light can travel in that medium. These instruments were not looking for anything spectacular, no brilliant flash, no cosmic firework. They were waiting for a whisper. Super-Kamiokande in Japan became the most iconic of these experiments. Located under 1,000 meters of rock in the Mizumi mine, its heart is a cylindrical tank filled with 50,000 tons of ultra-pure water. Suspended around this vast pool are more than 11,000 photomultiplier tubes, like a constellation of glass eyes gazing into the darkness. It is a place of absolute stillness. The water is so pure that it is almost invisible. Any stray particle, any contamination, could spoil the experiment. Inside this cathedral of silence, every proton in every water molecule becomes a potential messenger. There are roughly 1,033 protons inside Super-Kamiokande's tank, an unimaginable number, each one a clock counting down to its eventual decay. In principle, if protons are unstable, a few should collapse each year. Their death would produce a shower of lighter particles, a tiny burst of energy, a brief flash of Cherenkov light on the water's surface. But year after year, the flashes do not come. Instead, the detectors record other events. Neutrinos from the sun, ghostly particles from cosmic rays, even the faint signatures of supernovae exploding in distant galaxies. Super-Kamiokande has captured extraordinary glimpses of the universe, but not the one event it was built to find. The silence is not just empty data, it is the deepening of the mystery. As the years pass, the half-life estimates are pushed further back. First, physicists thought that perhaps protons decayed every 1031 years, then 1032, then 1033. Now the lower limit is beyond 1034 years, a span of time so long that it dwarfs the age of the universe itself by 20 orders of magnitude. If this estimate is true, then even if humanity observed every proton in existence, it would still see only a handful of decays in the entire history of the cosmos. The realization is sobering. No single human experiment could ever run long enough to confirm proton immortality. The best that can be done is to place stricter and stricter limits, to say that if protons decay at all, it must happen more rarely than anyone once believed. Physicists describe the experience with a strange mix of frustration and awe. It is like waiting for a ghost to appear that never does. Not because it refuses, but because it may not even exist. Some speak of the quiet as eerie, as though the universe itself is holding its breath. Others describe it as serene, a reminder that nature moves on timescales that are almost incomprehensible. But the data cannot be ignored. The longer the silence stretches, the more it reshapes the future of physics. Grand unified theories that predicted observable rates of proton decay have been ruled out one by one. New models must be built, new symmetries imagined, new mathematics explored, all because of the absence of a single event. And still, the detectors wait. Hyper-Kamiokande, a successor experiment now under construction, will be even larger, 100,000 tons of water watched by even more sensitive instruments. The hope is that, with a bigger experiment, with more protons under surveillance, the universe might finally offer a single, unmistakable clue. But there is no guarantee. It may be that the mystery will persist, that the particle will refuse to vanish for as long as humanity has the patience to look. This search has become more than an experiment. It has become a vigil, a long patient listening to the heartbeat of matter itself. And in that vigil lies a kind of reverence for what is. Being tested here is not merely the stability of protons, but the very narrative of time. The detectors ask the question every moment of every day. Will this be the instant when a particle lets go? When the universe allows one tiny piece of itself to finally vanish? So far, the answer has been no. The silence of these experiments is a strange gift. It forces science to confront the possibility that time may not erode everything, that there may be a bedrock of permanence beneath the flux. It forces a reconsideration of the ultimate fate of the cosmos, of whether the great dissolution is as final as once believed. And so, beneath mountains and oceans, the watching continues. Thousands of tons of water sit in perfect stillness, as though the Earth itself were holding a mirror to the invisible world. The photomultiplier tubes remain open, patient, unblinking, waiting for a light that may never come. The deeper humanity stared into the stillness of matter, the more the mystery seemed to twist and expand. If protons would not decay, if they refused to vanish despite decades of surveillance, then perhaps the story was larger than anyone had first imagined. The turning point came with an unexpected discovery. In 1998, deep inside the cavern of Super-Kamiokande, researchers announced the first conclusive evidence that neutrinos, those ghost-like companions streaming endlessly through the Earth, could change identity as they traveled through space. This was not supposed to happen. In the standard model, neutrinos had been assumed to be massless, immutable, eternal travelers that did not interact with the world, except through the faintest whisper of the weak nuclear force. But here was proof that they oscillated, that a neutrino born as one flavor could arrive at a detector as another. This meant one simple, devastating thing: neutrinos had mass. However small, however delicate, it was there. And if neutrinos had mass, then the standard model was incomplete. The revelation rippled through physics like a shockwave. If nature could hide such a fundamental truth about neutrinos for decades, then what else might it be concealing? Could the persistence of protons be part of the same hidden architecture, a design in which matter was meant to endure far beyond? What equations had predicted? The stakes were suddenly cosmic. The early universe had been a seething fireball of particles and antiparticles colliding, annihilating, erasing one another in a perfect storm. By all logic, it should have ended in a wash of radiation. No stars, no galaxies, no planets, no observers to wonder about any of it. And yet, for reasons no one fully understands, a slight imbalance allowed just enough matter to remain, enough to form everything that exists today. Could the stubbornness of the proton, its refusal to vanish, be part of the reason anything exists at all? Could this particle be the quiet guardian of a universe that prefers creation over emptiness? Physicists began to explore new possibilities. Perhaps proton stability was not an accident, but a feature of the cosmos, a deep symmetry that locked the building blocks of matter into a kind of timeless endurance. If so, then the fate of the universe might be dramatically different from what had been imagined. Consider the far future. Stars will burn their fuel and go dark. Black holes will slowly evaporate through Hawking radiation, their mass leaking back into space over unimaginable spans of time. If protons do not decay, then when all this has happened, when every furnace of light has been extinguished, matter will still remain. The atoms will drift endlessly, cold and quiet, but they will not vanish. The universe will never reach a perfect heat death. Instead, it will become a cosmic graveyard, filled with everlasting particles, monuments to the fire that once was. This realization is both wondrous and unsettling. It implies that time will never deliver the final erasure, that there will always be something left behind. The arrow of entropy may still point forward, but it will never reach its target completely. The universe will not dissolve into a uniform glow of energy, but into a thin dust of eternal matter scattered across infinite night. And then there is the more haunting possibility. If protons will not vanish, even after stars and galaxies have died, then perhaps the story of the cosmos is not a story of endings at all. Perhaps it is a story of endless persistence, a universe that refuses to fall silent. In the halls of physics, this deepened the tension. The Standard Model, once seen as the crown jewel of 20th century science, was clearly incomplete. Its symmetries were beautiful, but they no longer explained everything. Neutrino oscillations had proven there was more to discover. The silence of proton decay experiments only sharpened the question: what hidden laws are protecting matter from destruction? New experiments were proposed, larger than ever before, designed not just to watch for proton decay, but to probe the nature of neutrinos, dark matter, and other exotic particles. The mystery had expanded from a single question: do protons die? To an existential riddle: what is the universe made of, and why does it exist at all? The emotional weight of this moment is difficult to overstate. To learn that protons are stable is to confront the idea that the universe may carry its memory forever. The particles formed in the first seconds after the Big Bang may still be with us now, unchanged, older than galaxies, older than stars. They have watched the rise and fall of entire clusters of galaxies and will continue to exist long after the last photon of starlight fades. And so the question grows darker, more profound. If they refuse to vanish now, will they refuse even when time itself stretches to infinity? When there is no more energy to exchange, no more stars to shine, no more observers to ask questions? Will the universe end not with a flash, not with a sigh, but with a slow, endless persistence, a refusal to let go of the smallest pieces of itself? The silence of the detectors has become an oracle, whispering of a future so distant it lies beyond imagination. It is not a future of sudden death, but of infinite endurance, a future where the universe itself is haunted by particles that will not die. And this is where the mystery deepens most of all. Perhaps the refusal of the proton to vanish is not simply a quirk of physics, but a clue that reality is built, not to end, but to persist. That beneath the flow of time, beneath the crumbling of stars and the collapse of galaxies, there lies a hidden foundation that endures forever. For the scientists watching, this is both a promise and a challenge. A promise that there is more to discover, and a challenge to keep listening, to keep building, to keep seeking, even if the answer may never come in their lifetime. Because somewhere, perhaps, a single proton will decay. Somewhere, a single flash will light up the detector and tell humanity that the story has an ending after all. Until then, the universe holds its breath. As the silence of proton decay experiments stretched on, theorists began to search for explanations not in the data that was seen, but in the symmetries that might lie hidden beneath the surface of reality. the Standard Model had carried physics far, a masterpiece of mathematics that predicted the Higgs boson decades before it was found, a framework that explained almost every interaction ever measured, and yet it was clearly incomplete. Physicists turned to what are called grand unified theories, GUTS as they are known, sweeping frameworks that attempt to merge the strong, weak, and electromagnetic forces into a single, elegant description. In these models, protons are not immortal. They should eventually fall apart, their quarks rearranging and releasing their energy in a final flash. The predicted timescales are staggering, 10 to the power of 34 years or longer, but not infinite. In this view, proton decay is not forbidden, merely delayed beyond the reach of any human experiment. This idea carries a kind of bittersweet poetry. If protons will eventually decay, then even the very building blocks of atoms are temporary. Every molecule, every cell, every star would someday disassemble itself into radiation. Matter would not last forever. The universe would move toward a true heat death, where no memory of its luminous youth remains. But each year that passes without a single observed decay forces the theoretical predictions further outward to longer and longer half-lives. It is as if the protons are defying expectation, clinging to existence more tightly than the equations allow. Some theorists propose that there may be additional symmetries at play, subtle rules of the cosmos that stabilize matter against disintegration. This is where the idea of supersymmetry enters, one of the most ambitious proposals of modern physics. Supersymmetry suggests that every known particle has an unseen partner, a superpartner with a different spin. These hidden particles, if they exist, could help explain why protons are so stable. They might act as guardians, preventing the decay channels predicted by simpler theories. The search for supersymmetric particles has been one of the major goals of particle accelerators like the Large Hadron Collider. If even one of these partners could be discovered, it would open an entirely new chapter of physics, a signpost toward a deeper, more unified description of nature. But so far, like proton decay, these particles remain elusive. The implications of proton stability stretch far beyond particle physics. They reach into cosmology, into the question of the universe's ultimate fate. If protons never decay, then the future will not end in a flash of annihilation, but in something far slower and stranger. In the farthest imaginable epochs, stars will exhaust their fuel and fade. White dwarfs will cool to black embers. Neutron stars will become cold, inert spheres. Black holes will slowly evaporate, their mass dissolving into Hawking radiation until even they vanish. And yet, if protons are truly eternal, the atoms that survive will drift forever through a universe that has gone completely dark. This is not the tidy heat death predicted by 19th century thermodynamics, where everything ends in a perfect equilibrium of radiation. It is a lonelier fate, a cosmos that continues to exist but grows colder and emptier with every passing aeon. The universe would never erase itself completely. Instead, it would become a museum of frozen particles, each one a relic of a time when space was bright with stars. And here, the mystery becomes philosophical. If a proton created in the first second after the Big Bang is still here, unchanged, then it is a time capsule, a messenger from the dawn of existence. It carries with it the memory of that first fireball, the conditions that shaped everything that came after. Perhaps this is what it means for the universe to remember. Perhaps the persistence of matter is not just a feature of physics, but a kind of cosmic testimony, a refusal to let the story be forgotten. Some thinkers have speculated that this memory might even point to a deeper truth about time itself. If the smallest pieces of matter can endure for nearly infinite stretches, then perhaps time is not the destroyer it seems to be. Perhaps it is simply the stage upon which endurance plays out, a vast canvas on which the universe sketches patterns of persistence. But there is another way to read this silence, and it is darker still. If protons never decay, if matter never truly dies, then the universe may be trapped in an eternal twilight, unable to reset, unable to begin again. creation would have been a single, unrepeatable act. There would be no cosmic rebirth, no cycle of renewal, only the slow, infinite continuation of what already is. This is the paradox of proton stability. It offers hope that something endures, that the universe does not vanish into nothing, but it also suggests a future where the story never truly ends, where there is no final act, only an endless coda stretching into eternity. For now, humanity can only wait. The detectors sit in their caverns, silent and watchful. The theories continue to evolve, pushed and reshaped by the weight of every unanswered question. Somewhere in the depths of reality, the truth is written, whether in the equations of a grand unified theory, in the hidden particles of supersymmetry, or in a symmetry so subtle it has yet to be imagined. And above it all, the protons remain. Each one a stubborn fragment of the Big Bang, each one a reminder that the universe still holds its secrets close. Until the first decay is seen, until the first flash of light announces the beginning of the end, the cosmos seems content to wait, to hold its breath, and to let its story unfold one imperceptible moment at a time. Beneath mountains and under oceans, in abandoned mines and frozen polar deserts, humanity continues its vigil. The search for a vanishing proton, for even a single flicker of its decay, has become one of the longest-running experiments in the history of science. Entire generations of physicists have passed the torch, building ever larger instruments, refining ever more sensitive techniques, and still the detectors remain silent. At the heart of this quest stands a cathedral of physics, the vast chambers of Super-Kamiokande in Japan. Carved into a mountain and filled with 50,000 tons of ultra-pure water, its walls are lined with 11,000 golden photomultiplier tubes, each one waiting for the faintest pulse of Cherenkov light. It is a machine built to see what the universe hides best: the death of a proton. For decades, this detector has stared into the darkness, listening for a flash that has never come. But science is not easily discouraged. Even as Super-Kamiokande continues its watch, a successor is rising, Hyper-Kamiokande. 10 times larger, equipped with more sensitive detectors, it will push humanity's ability to detect proton decay to unprecedented limits. Each year of data will stretch the lower bounds of the proton's half-life further, pushing the mystery deeper into cosmic time. Across the world, other detectors join this chorus of observation. The Deep Underground Neutrino Experiment, DUNE, is being assembled nearly a mile below the surface of South Dakota. 4 enormous cryogenic tanks will hold 70,000 tons of liquid argon, turning an ancient rock cavern into one of the most ambitious particle detectors ever built. Though its primary mission is to study neutrinos, its scale will make it a silent witness to any proton decay that may occur in its depths. And then there are the experiments that use nature itself as a laboratory. Cosmic rays, particles accelerated to almost unimaginable energies by distant supernovae and active galactic nuclei, strike Earth's atmosphere with forces that no human-built collider can match. By observing these natural collisions, scientists hope to glimpse processes that might hint at proton decay or reveal physics beyond the standard model. Far to the south, under a kilometer of Antarctic ice, another instrument listens, not for decays, but for the ghostly passage of neutrinos born in the most violent corners of the cosmos. The IceCube Neutrino Observatory transforms a cubic kilometer of ice into a transparent telescope. When a neutrino collides with an atom, it produces a faint flash of blue light captured by thousands of sensors frozen deep below the surface. Each flash is a whisper from across the universe, carrying clues about the nature of matter and energy at the highest scales. These tools together form a network of cosmic ears and eyes, patiently gathering evidence. They are monuments to human persistence, an acknowledgement that the answers may not come quickly, or even within the lifetime of their builders. But this is what makes the search so profound. Proton decay, if it exists, may be so rare that no single experiment will ever see more than a handful of events. The timescales involved are longer than the age of the universe itself. Each year of null results does not end the quest. It simply shifts the boundary of what is possible. And so, the work continues. Detectors are upgraded, new observatories are proposed, and the data streams accumulate, bit by bit. In particle colliders like the LHC, quarks are smashed together at nearly the speed of light, revealing new constraints on the forces that hold them bound. In underground laboratories, silence becomes data, and that data reshapes theory. It is possible that the final word on proton stability will never come from a human experiment. Perhaps the universe is simply too patient, its processes unfolding on scales beyond human imagination. If the proton's lifetime truly stretches beyond 10 to the 36th year, then no detector could ever measure it directly. In that case, the quest itself becomes the point, an infinite watch, a demonstration of curiosity that endures as stubbornly as the particle it seeks to understand. There is a quiet nobility in this pursuit. Each experiment is not just a scientific device, but a message to the future. We were here, we wondered, we tried to listen. Even if the answer comes in a billion years, there may be records left in stone and data, waiting for another civilization or another species to discover what we could not. And still, there is always the possibility that tomorrow, or next year, or a century from now, one of these machines will see it. A single flash, a single proton breaking apart after an age-long silence. That one event would rewrite textbooks, confirm decades of speculation, and mark the beginning of a new understanding of reality itself. Until that day, the detectors keep watching. The mountains hold their secrets. The ice waits in perfect stillness. The universe continues to whisper its truths, one elusive particle at a time. Humanity listens, not because the answer is guaranteed, but because the question is too beautiful to abandon. In a universe governed by impermanence, the refusal of a single particle to die feels almost rebellious. Everything in nature bends toward decay. Stars ignite and collapse. Galaxies scatter. Even light itself stretches, its wavelengths growing, longer as the fabric of space expands. Time seems to erode all things, grinding creation down into a final, featureless smoothness. And yet, in the heart of every atom, the proton persists, as though reality itself has chosen to leave behind a fragment that cannot be erased. This endurance carries a strange beauty. It is as if the proton has become the guardian of existence, holding memory in its smallest quarks. In its silence lies a promise that something, no matter how small, will resist the entropy that devours all else. The very atoms that form oceans, mountains, and the bones of living creatures are built upon this defiance. Without it, the universe would have dissolved into radiation before the first stars ever shone. In this way, the proton becomes more than a building block of matter. It becomes a metaphor for persistence itself. It is what allows the cosmos to tell a story at all, to weave hydrogen into stars, stars into carbon, carbon into life. Every breath ever taken, every thought ever thought, begins with this quiet particle that refuses to vanish. The symmetry is haunting. Human beings, too, live under the shadow of entropy. Their lives are brief, their civilizations fragile, and yet they continue to reach outward, to write, to build, to wonder. In this light, the proton feels like a reflection of the human spirit. Both exist in defiance of oblivion. Both endure as long as they can, clinging to meaning in a universe that offers none by default. Perhaps that is why its silence feels so moving. The absence of decay is not just a scientific puzzle. It is a kind of cosmic reassurance that the story of existence will not be cut short too soon, that there will be time enough for galaxies to form, for life to arise, for consciousness to wonder at the stars, but the vision stretches far beyond the present age. Imagine the deep future, when the Milky Way has collided and merged with Andromeda, when the last red dwarfs have burned away and only black holes remain. Imagine waiting still longer, until even those black holes have evaporated into nothing but radiation. By then, the universe will be an expanse of unimaginable darkness, silent and cold. And still, if the proton is truly eternal, some of them will remain, drifting through space like the last notes of a song long since ended. In that darkness, there will be no observers left to measure them, no eyes to see, no ears to hear, but the particles will still be there, carrying with them the memory of the Big Bang, unchanged since the first second of time. They will be the final witnesses, the last storytellers of creation. And if one day they too decay, it will mark the closing of the last chapter. The universe will finally surrender to perfect equilibrium, and all record of its luminous youth will be gone. But until then, the proton's defiance continues. Each one is a quiet protest against nothingness. Each one a symbol of the fact that existence, for reasons perhaps beyond understanding, still endures. As the music of creation fades, as the lights of the stars go out one by one, these tiny fragments of matter will remain, unbroken, unyielding. They will drift across the void in silence, not asking to be seen, but simply continuing to be. And in that endless night, the universe itself will be held together by a single idea, that not everything must vanish. Perhaps it is not the stars, but the smallest fragments of matter that are the true storytellers of eternity. Fade out, the screen darkens, a final, lingering shot of a lone proton, suspended in infinite blackness, glowing faintly with the memory of the Big Bang. The final image fades, leaving only darkness. The narration returns, calm, almost reverent. The proton drifts on, carrying the last memory of creation. The universe grows silent, but its story is not yet over. And so, a question remains. If even the smallest fragment of matter can defy eternity, what might still endure within us? Fade to black. Music falls quiet, like the breath of the cosmos itself.